Okay, off we go. So last time we were talking about cross products. We were most of the way done. So just a few more things to say. By the way, you'll notice that I did already assign 1.4 in the sense that in the sense that I put 1.4 as something that we completed on Friday. We didn't complete it on Friday, right? But we were close enough that I thought it was reasonable to indicate it thus so that you would be encouraged to start those exercises over the weekend, which I think we had covered enough for y'all to be able to start those exercises. Okay, but let's finish it now and move along. So we've proved from the definition of cross product that we gave that the cross product is the exact unique vector that satisfies these three conditions, right? We've talked about all three of these results. I guess I didn't prove them, right? But I've stated those results, and the proofs are there in the notes if you care to read them, but you don't have to. So this is an interesting way to define cross product, sort of an alternative definition. This is what the book uses as the definition, as opposed to giving a formula like we did, and then deriving these geometric properties. The book says, let's define the cross product as the unique vector that has these three properties, and then they laboriously derive the formula that we started with, right? So there's two totally different ways of doing it, and there's other ways of doing it as well. They're also very cool, and so every book, every instructor is going to have their preferred way of doing things. So anyway, I think that's kind of a neat feature. A couple more quickie things to say. Do be aware, cross product is kind of a product. I mean, what is a product anyway? It's product-like in a certain sense. If you write down some of the algebraic properties, algebraically kind of behaves like a product, but not 100%. And so in particular, cross product is not commutative. And that's an easy one to mess up, right? If you're thinking multiply, like good old regular, elementary school type multiply, when you're doing the algebra of cross products, you're going to accidentally forget this, and then you're, it's a significant problem, right? Okay. All right. So yeah, be aware of that. And here's some additional points that I think are worth mentioning. I like to make the observation that cross product is linear. Now, what I just said is technically not quite true. Linear means something that acts on a vector in such a way that linear combination in, linear combination out, however you want to say it, right? Cross product acts on two vectors. So, it doesn't really make sense the way I said it, but this is how people describe the following property, and that is that if you fix some vector, let's say A, and then if you say, look, I'm going to use that vector, I'm going to go around with that vector, and I'm going to cross with A to whatever vector I run into. Okay? Crossing with A, that's what I do. I just go around, you show me some vector, I'm going to cross it with A. Right? That action is a function because whatever x you give me, I can do that action. I can cross it with A. Right? And this function is linear. Right, so this t function, the action of crossing with a fixed vector A, is linear. And you can see that in how we write it down in this equation here, the action of crossing with A. Here, let me put the parentheses to make it a little bit better, a little bit more visible. The action of crossing with A, I'm rewriting as t there, and notice all this bit of algebra that kind of looks like sort of a distributivity and a sort of an associativity of sorts, whatever, is really just saying when you put a linear combination into a cross product, what you get out is a linear combination of individual cross products. So cross products are linear in that sense. So, kind of a cool fact. It works on both sides, by the way. So, the way I wrote it here, because it it looks cooler on the page when you have the fixed vector A on the left, because that's why we write what functions look like. We write it on the left. It's just the way we do things. But if you do it on the other side, if the action of crossing with A is on the right, that is a different function. But that, too, is also linear. Okay. How are we doing? Everybody good? Yeah.
By linear, you mean linear combination?
A linear, it's a linear transformation. Yeah. Right. Absolutely. And I'm going to say a few more words about that in a bit here. Another thing to heads up, just be aware, I don't remember seeing this in the book. I might have just missed it. But cross product's not associative either. So it's another uncomfortable, it's an easy thing to kind of be a little too kind of casual and familiar with, hey, this is how algebra works, and to think of it as multiply, to treat all multiplies like they all behave the same. They really, really don't. And cross product does not have this property that, notationally on the page kind of feels like it ought to. It absolutely does not. Okay, a couple of quick applications. That's not really perhaps the right word. We're not going to solve any problems here, but let me say maybe I should call these manifestations. So I have defined something that is a formula that has some nice mathematical properties, and there is a concern that some of you may have that is this just a sort of a mathematical game that that mathematicians like to play, and we're learning to play some game that for whatever reason. And I think a pretty good response to that is that no, it really very naturally manifests in the real world. When I say manifest, what I mean is if, for example, if you have an axle and you want to turn that axle and you have an arm, let's say, sticking off of that axle, and you're going to, apply a force, right? So here's the direction of the force that you're going to apply to that arm that's attached to that axle. How hard are you twisting? What is the torque? Well, it turns out that the torque there is computed by, let's see, I've lost track of my colors. R cross F. In particular, it's a cross product. Right? So mathematicians did not impose this on the world, right? The world was long since made before we even started scribbling, right? So cross product arises naturally in the physical world. I think that's kind of cool. Y'all probably remember from physics classes. If not, no sweat. You'll see it in future physics classes, probably. If you're most of y'all are engineers, I think. By the way, just for my curiosity, engineers, show of hands. Practically all of you. Okay, not all, but most. So yeah, you'll learn about magnetic fields a little bit. Magnetic fields are weird. By the way, we're going to do a bunch of math later in this semester. Chapters 6 and 7 in this book are about some very cool, very sophisticated, though, ideas of divergence and curl and flux and these kinds of things that are extremely powerful tools for studying magnetic fields and electric fields. And so if you haven't taken an E&M class yet, but have to take E&M next semester or whatever, you're going to have an unfair advantage over everybody else in the class because you're going to know lots of mathematical tools that, most Physics 152? Yeah, most Physics 152 students don't know. And so I had that advantage when I was in college. I had already had multi by the time I took E&M, and major advantages. Anyway. Okay, so here's one curiosity about magnetic fields. Magnetic fields, very often written with the letter B. Right, so magnetic field B. And suppose you have a particle moving through that magnetic field with some velocity. it turns out, and don't ask me why, right? I mean, nobody really knows why the physical world was put together the way it is. We observe, we notice relationships and connections between things, we notice that certain more fundamental observations or forces or whatever we decide to call them seem to cause other phenomena to happen, but nobody really knows why, right? So, for whatever reason nobody knows, when a charged particle moves through a magnetic field like that, there is a force that is created, and that force is computed with a cross product. So again, that is a physical manifestation of the cross product that, I didn't do it, right? Math community did not make that happen. This existed before. This was true before we knew how to say it. Okay. All right. Okay, the very last thing in 1.4, this is a students to read. I'm going to say a couple of quick words, as I often will do for these kinds of things. The cross product mostly is a three-dimensional thing. There is a higher dimensional cross product that y'all are going to play with on one of the homework exercises. Maybe you already have one of the later homework exercises, if I remember correctly. I had the details. I'm sorry, I don't remember. But there is a generalization to higher dimensions. A little harder to talk about. But the regular old binary operation, 2 vectors in, 1 vector out, called cross product, is only in 3 dimensions. There is a similar thing in 2 dimensions. It's not the same, but it has certain similarities. It's called the wedge product. Here's the definition. The wedge product is computed by a determinant. You just take the 2 vectors and make a matrix out of them and compute that determinant. And it has some kind of cool properties. It's kind of like a triple product in some ways. It's kind of like a cross product in some ways. And it's a nice little operation to have available to you, because sometimes this is exactly what you need. When we get into chapter 6, the wedge product is going to end up being a very convenient notation to use for representing some of those objects that we're going to talk about then. It's not a particularly common notation, but I think it's cool, and I want y'all to be aware of it, and it is going to come up again a little bit in chapter 6. Okay, y'all can read the rest of this. Okay, moving on. Section 1.5. Just a reminder, we are moving quickly, I know. The reason, again, we're moving quickly now is because of tough choices and all that. And once we get to chapters 6 and 7, even 5, right? Chapter 5 is also very challenging, right? There's a lot. It's just more ideas. There's more going on, and I think you're going to feel like the level of even though we're going to be going slower later on, I think you're going to find the level of challenge will actually be a little higher. So heads up about that. And that's why we can't spend too much time on this stuff. But let's talk about the equation of a plane real quick. If you give me a plane, and if you're going to tell me what plane you're talking about, you're going to have to describe that plane in some way. Let's suppose that you describe it by way of a normal vector. So a vector perpendicular to the plane, and a point that's contained by the plane. You give me a point, you give me a normal vector, there is a unique plane that describes. Okay. The question is how to come up with the equation of a plane. Let me remind you, and I think it's really important to keep track of, when I say the equation of a plane, remember that an equation is a point tester. Right? Don't think of it too casually as it's algebra you write down that some ambiguous way relates to the object you're describing. An equation is a point tester. You put a point in there. If the equation works, then it's in the object. If the equation doesn't work, then it's not in the object. So when I say we want an equation, I mean we want a point tester. How would I test a point like that, which, as I've drawn it, appears to be in the plane, but as far as I know, maybe it's up here. Right? I don't know which of these cases I'm looking at. If you give me some random point, is it in the plane? Is it not in the plane? How do I tell? Right? So the big idea is to subtract the point that you're trying to test, R, subtract R naught, the point you were given. If this is in the plane, and you subtract a point in the plane, that difference would be parallel to the plane. And that's an if and only if. Because if the point you're testing is not in the plane, and you subtract a point that is in the plane, then that difference would not be parallel to the plane. Yeah?
Could you explain the difference between the right next to the R vector, that symbol, versus the symbol that's next to...
You're talking about this versus this?
Yes.
Yeah. This one down here is a standard symbol, meaning that this point is an element of that set. This is me being cute. I turned it around the other way because this point is an element of that. Sure. Yeah, it's just I just turned it around backwards. Yeah, sorry about that. Does that make sense, though?
Yeah.
Does that make sense to everybody else? Okay, cool. Yeah. Yeah, it's a little bit of an abuse. Yeah, yes.
When you said points subtract from the other point, do you mean they're vectors?
Yeah, well, that's right. So remember that there is a one-to-one correspondence between points and vectors. Right? If you give me a vector, I can talk about the point where the head would be if the tail was at the origin, and then vice versa. If you give me a point, I can talk about its position vector. Very often it's convenient to conflate those just in terms of various operations. It's tedious to constantly talk about, well, I don't mean the point, I mean the vector corresponding to the point and stuff like that. So yeah, we tend to kind of sweep that distinction under the rug. You do have to keep in mind what exactly you're talking about, and you do have to keep strict to that correspondence. It has to be strictly that correspondence. So when I say subtract a point from another point, yes, what I meant is take these points, view them as vectors, do the subtraction, that difference will then be another vector, and that's this vector here. Does that make sense? Yeah. Okay. Yeah, so this is our test. Our test is to look at that difference and see if it's parallel to the plane. Notice that the given normal vector being perpendicular to the plane, this is parallel to the plane if and only if it's perpendicular to the normal. And perpendicularity, perpendicularity, this being perpendicular to that, we can represent with the dot product being 0. I'm being deliberately sloppy. I'm gonna fix my math crime in just a moment. But for the moment, perpendicular, dot product is 0. Is that cool? Which, by the way, gives us the equation of the plane, because this is algebra, which you can, for just sort of cleanliness, you can move terms around, distribute, subtract, whatever. And rewrite with this equation right here. So this is a point tester. If you give me some point R, x comma y comma z, you want to know if that's in your plane, plug it in there. Keep in mind that n and R naught were all given. Those were the givens that described the plane in the first place, and that's your point tester. Everybody on board? Okay, let's fix the sloppiness. Let me confess to my math crime. Anybody notice my math crime?
Yep.
What is it?
Orthogonal versus perpendicular.
Yeah, exactly. Okay, good catch. Absolutely. So, it's convenient to be sloppy about that, and you can get into trouble. In this case, I claim it actually worked out. We look at this orthogonality here, And let's just ask, well, wait a second. Orthogonality and perpendicularity are only the same if we know the vectors are not 0. Well, can that normal vector be 0? Keep in mind, its job is to point in a direction that's perpendicular to the plane. It has to point in a direction. It can't be 0. Otherwise, it just wouldn't be able to do its job. Does that make sense to everybody? Okay. Sweet. Okay, so that one we don't have to worry about at all. What we are going to have to worry about, though, is this difference vector. That difference vector could be 0. Specifically, if the point I wanted to test is R0 itself, then that is the 0 vector. And now, oh gosh, wait a second. Okay, I started with perpendicularity. I sloppily switched to orthogonality. 0 is on the table. Did I blow it? And the way we address that is we just ask the question, all right, well, this, if R was R0, if I wanted to test whether R0 is in the plane or not in the plane, what should the answer to that question be? Well, it's given. It's given to be in the plane. So I want R0 to pass the test. R0 has to pass the test. So in fact, not only is perpendicularity, not only is orthogonality an acceptable sort of rewrite, it's a mandatory rewrite. I need to allow R minus R0 to be 0. Does that make sense to everybody? If I were to say that the test is, I need R minus R0 to be perpendicular to N, that would be wrong, because that would disallow R0, which I can't do. Okay, all right. Okay, cool little observation to make is that, and by the way, real quick, I'll point out this is my favorite form of the equation of a plane. On the other hand, you can take, whatever coordinates you want to use for n, and you can kind of, crank out the dot product there. Keep in mind that x comma y comma z is what r is. The point you're testing, x comma y comma z. So you can just crank out that dot product. You get ax plus by plus cz. The right-hand side, keep in mind that both of these were given, so these are known, and when you dot them, you're going to get some number, whatever, let's call it d. So this is an equivalent formulation here, right? A lot of students prefer this bottom form because it's familiar looking. Everything's written in terms of coordinates. Coordinates are familiar. Seems like maybe this is the simplest form. Let me just remind you of a couple of things. First of all, coordinates are useful, but are ultimately not the main thing that we're interested in. They're tools that serve a purpose, and in some cases, that's a useful purpose. That's nice when it comes up, right? So fine. But ultimately, what are we actually interested in this class? Well, we're interested in connecting ideas to other ideas and understanding reasoning and understanding why things are true and stuff like that. Developing a geometric understanding of how these ideas relate to those ideas, that kind of thing. And honestly, I think this top equation is quite a bit better than that, than this in that way. So this not only is a test, this shows how the normal vector plays a role in that test. Right? Arguably, this form up here, maybe this is the best one. Because here you can literally see the orthogonality coming up as the main tool for the test. Right? So I would like to encourage, again, it's tempting to think in terms of computational convenience and plug and chug and this kind of thing, but keeping in mind that we're interested in ideas, and fundamentally the objects we're most interested in are points and vectors, not coordinates, right? These are really quite a bit better. This is written in arguably kind of awkward terms in a way that conceals some of the ideas. And I think that's a minus for your consideration. Okay, it is cool, though, I think a neat fact, if you have this form of the equation, notice you can just read right there as the coefficients, you can just read what the normal vector is. It is a really neat fact. Whenever you have an equation of a plane given to you, just peel off those numbers, boom, there's your normal vector. Everybody on board? All right. Okay, real quick example. Let's see here. Let's suppose we are given these 3 points, which I'm going to draw, let's say like that. And the question is to find the equation of the plane that contains them. So here's the plane that contains them. I want to find the equation of that plane defined by those 3 points. Everybody see the question? Okay, all right. So there's a puzzle aspect to questions like this. You're given certain information, you want to find certain other information. The way this question's been phrased, notice we were given what I'm going to call some algebra. We were given coordinates of 3 points, and we were asked to find other algebra, namely a particular equation. The way I like to do this is to think geometrically. So I would rather rephrase this as geometrically, what do I have? What can I geometrically quickly infer? Well, again, I was given these 3 points. And now what do I need? Well, wait a minute. We're looking for the equation for the plane. In order to find the equation, I need a normal vector and a point. We got points. We got plenty of points. Pick one, whatever. We got points coming out of our ears, right? Plenty of points. Doesn't matter. But I need to find this normal vector. So instead of thinking of this as algebra given, algebra to be found, think of this as geometric objects given, and there are geometric objects to be found. And now we're basically playing a geometry game here, and given these 3 points, how do I find that purple vector? And there's, in this case, pretty straightforward solution. You pairwise subtract to get a couple of vectors like this. And then notice that because they are parallel to the plane, that means that their cross product is perpendicular to the plane. Everybody see the geometry there? Okay. So I myself think it's much easier to make this connection by looking at the picture, right? I see these points. I can basically see these edge vectors. It leaps off the page to me that these are parallel and that's perpendicular. That just almost makes me think cross product, right? Your geometric intuition can be your guide to take you through, to tell you basically, what your algebraic process needs to be. So that's what I encourage. Okay. Is everybody okay? Everybody are happy? Okay. All right. Okay, this next one I think is an underappreciated fact. I wish this were more heavily emphasized. I don't think, again, I can never remember, but I don't think this is explicitly stated in the book. I think this is worth stating. Really cool fact. Very easy little cool fact. If there's no y's in the equation of a plane, now you'll notice I wrote 0y here. That's just so that I can explicitly indicate that there are no y's there. And of course, in practice, if there are no y's in the equation, what you're probably going to see is that just literally they won't put anything. Why would you put 0y there, right? That's silly. So if there are no y's in the equation, you get a really nice little conclusion, and that is your plane has to be parallel to the y-axis. I meant to do this in the highlighter. The plane is parallel to the y-axis. And I'll tell you, before I show you why this works, I want to explain why I like this result. And it's because the cost, right? What does it cost me to try to investigate whether I can use this theorem? It costs me nothing. I just have to eyeball glance and see if I see any y's in the equation. How long does that take? Quarter of a second? Nothing, right? Practically free to check the condition on this result, and then what I get out of it is a geometrically useful piece of information. Hey, this plane you're looking at, hey, it's parallel to the y-axis. That's geometrically useful fact, right? So it's an opportunity for almost free information. All right, now let's see why it's true. Go through the reasoning here. Got the equation of a plane. Keep in mind, you take those coefficients, as we discussed up here, right, whoops. You take those coefficients, they just straight up give you your normal vector. Okay. So that's what I'm going to do here. You take those coefficients, A, 0, and C. Well, that's my normal vector. All right. Next observation. E2, our second standard basis vector, which, by the way, you can draw. Keep in mind, vectors don't have location. You can draw them wherever you find convenient. I find it aesthetically a little bit more convenient to draw it over here. Whatever, doesn't matter. E2, 0, 1, 0. Pretty easy to look at the numbers and see that this dot product is always going to be 0. That's how the numbers work. That means that these two vectors are perpendicular. Is that cool? So altogether then, we have two things. I have, let's see here, I guess it's, okay, let's clean it up. What I've shown then is that my plane is perpendicular to the normal vector, but also that the normal vector is perpendicular to the y-axis. Now, here we have to kind of think through some geometry. If your normal vector, if you've got a plane, a perpendicular normal vector, and if that perpendicular normal vector is perpendicular to the y-axis, you got to use your geometric intuition, visualize what this looks like. It follows that the plane has to be parallel to the y-axis. Everybody see that? This is a geometric appeal. By the way, there's going to be a lot of geometric appeals in this class. Geometry is just hard to avoid in multivariable calculus. So, yeah, nice conclusion then. We get the parallelness that we need. Okay. All right, here's an exercise. If you're in the market for a practice problem, or if you want to test yourself, do you really understand the argument that I made here? A great way to test it would be to set this aside, take a clean sheet of paper, no cheat sheets, no notes. State and prove the equivalent result for the x-axis or the z-axis. Totally works. Right? There's nothing peculiar about the y-axis here. If there's no x's in your equation, that plane is parallel to the x-axis. State that, write it down, draw the picture, try to reproduce what would that proof look like. It's going to be a lot like this, just in a different direction. It's worth a try. Everybody good? All right, here's another one. So I'm given the equations of a couple of planes, and I want to parameterize the line that goes through a certain point and that's parallel to both of those planes. So, again, I'm given some algebra, and I want to find some algebra. I'm given two equations. I want to find a parameterization. Again, try to think of this geometrically. Try to think, what does the given algebra produce for me geometrically? And then, likewise, geometrically, what am I going to need to produce a parameterization? And then play geometry games. So these equations give me these vectors. Right? Again, reading the coefficients. Right? Really neat fact, those coefficients will always give you an appropriate normal vector. So 1 minus 3, 1. That's this normal vector. So that's what I have. Oh, well then, of course, let's see, I also have that, this point. So that's what I have. Let's see here, how to make a parameterization. How do we parameterize a line? Flashbacks to last week. To parameterize a line, you need a point on the line. We already have that. Sweet. And then I need a direction vector. I need a vector parallel to the line. Everybody on board so far? So the breakdown then is, this is what I have, this is what I need. Right? I have these geometric objects, I need this geometric object. And again, it's a puzzle. There's always a puzzle aspect to these kinds of questions. What tools do I have? Do I want to compute a projection of something maybe, or do I need a component? What? How can I get from these things to this thing? You got to figure that out. In this case, it's pretty straightforward. Again, you can probably see it coming. Cross product is the perfect tool. These two normal vectors that I have, the cross product gives you that v vector. Yeah.
I just didn't understand how you come up with N1 and N2.
Yeah. So I'm right. So I'm using this observation that I made here, that if you have an equation of a plane, right, you can just look at those coefficients. That will always give you, with ABC, whatever that vector is, that will be your normal vector, or it will be an acceptable normal vector. So that's what I did down here. I looked at these equations, like this equation, x minus 3y plus z equals 0. Well, 1 minus 3, 1 are those coefficients. That's how I got into. Mm-hmm. Is that all right?
Yeah, but it doesn't matter, like the other side of the equation.
To find the normal vectors? No, it doesn't. Yeah, that's good observation. So let's go back to here. What role does D play here? Well, you can see D it depends on the normal vector, but it also depends on R naught. So that D will basically distinguish this plane from a parallel plane. Same normal vector, different, going through different points. Yeah. Right. Okay. Okay. Cool. So, now in both of these arguments, I made, there's a certain common feature to the reasoning that I used here. I can't get that to erase. Certain common feature. I argued that if this is perpendicular to that, and if that is perpendicular to that, the knee bone's connected to the leg bone's connected to the hip bone. You know what I mean? It's put them together, and I get a relationship between the plane and the y-axis. And this is what I like to call a transitivity. It's just a word, right? But when you connect two arguments into a single thing, sometimes that's called a transitivity. So there's a transitivity there. And then likewise, down here, there was a transitivity. Let's see how to do it. These normal vectors are perpendicular to these planes. These planes are parallel to that vector. Combine them together, and it allows us to conclude that these normal vectors have to be perpendicular to that v vector. So again, kind of a transitivity that was implicit in that argument. Okay, so here's the point. Beware. These transitivities that look like they ought to be true are not always true. You have to think through, wait a minute, is that true? You got to just consult your geometric intuition. Make sure that you're comfortable that they're true before you go writing stuff down that just sort of symbolically appears to be true. So, for example, sort of feels like that if V is parallel to P, and if P is parallel to W, I mean, if this is parallel to that and that's parallel to the other, kind of feels like V should be parallel to W. Just in terms of how it lays on the page. Right? There's a seeming sort of transitivity there. But it's nonsense. Because V is parallel to that plane P. That plane P is also parallel to W, and yet these two vectors have no relationship. Nothing. They're not necessarily parallel. They're not necessarily perpendicular. There's basically nothing we can say about them. Everybody see what I mean there? So, you have to make arguments like this sometimes. This is a valid transitivity because if a plane is perpendicular to a vector, and if the vector is perpendicular to another, it really is true that that's got to be parallel to that. That's just, you think through the geometry, yeah, that just has to be. Right? So you do have to make transitivity arguments. Just be aware, again, sometimes they fail. And then here's another one down here. Planes being perpendicular, that there is no transitivity there. Right? P is perpendicular to Q, Q is perpendicular to R. P and R have no relationship. Everybody see the danger on this? Okay. So, I suppose it would be possible for me to write down a complete list of all possible transitivities involving lines and planes and vectors and parallel and perpendicular and combining to make parallel or perpendicular in 2 dimensions versus in 3 dimensions versus in higher dimensions. It would be dozens and dozens of possible transitivities, and I could write them all down and I could tell you exactly which ones are true and exactly which ones are not true. And I don't think anybody wants this. Okay, that would be a lot of tedium. I think the much more natural and reasonable way to approach this situation is to say, just be careful, right? If you cite a valid transitivity, cool, all good. The only asterisk is, of course, and this isn't, hopefully this is not too big of an asterisk, you do have to be right. You know what I mean? I mean, if you make a claim along the lines of this nonsense, well, it's just wrong, right? So the thing that's going to distinguish this wrong from this right is going to be your geometric instinct, your geometric intuition. Right? So be careful and be on the lookout for these kinds of problems. Okay. How do you parameterize a plane? We've talked about equations of planes. We've talked about parametrizing curves. We have never to this point said anything about parametrizing a surface of any description. Right? Okay. But we can still do it. We can keep in mind what a parameterization is. A parameterization is a point generator. If I know a point on a plane, and if I know a couple of vectors parallel to that plane, and I want to know how can I crank out and start producing a bunch of points? How can I generate a bunch of points that are on this plane that, goes through the point A and is parallel to these vectors V and W? By the way, anybody having flashbacks to that homework exercise from section, I can't remember if it was 1.1 or 1.2, right? But y'all used a construction kind of like this to generate a parallelogram. Just take your starting point and add appropriate multiples of those given vectors V and W, right? And green plus blue will always produce a point on the plane. Does that make sense to everybody? By the way, I got questions in both of my previous sections. This is a very reasonable question. It looks like I drew a parallelogram, right? And it's really hard to draw three-dimensional things and make it clear exactly what you're talking about. Usually when we draw in space, when we draw a plane in space, what we actually draw is what would a rectangular subset of that plane look like? And so, I draw the edges just because I have to draw something so you can see the thing I'm trying to describe, right? I got to put the pen to the page somewhere. And so, typically we think of a rectangle inside of that plane and then draw what that rectangle would look like. Almost lost the glasses. It makes it look like it's a parallelogram. And that's not my intention here. This is intended to be a plane that extends infinitely in all directions. How would I draw that, though? You know what I mean? Okay, so this always generates points on that plane, and you can see that it does so with two parameters, S and T. Any value of S, any value of T will always produce a point on the plane, and every point on the plane will be produced by some values of S and T. So it's just like a parametric curve. It's just that there's two parameters instead of one, making a two-dimensional plane instead of a one-dimensional curve. How we doing? Okay. All right, quick example. Probably recognize this example. These points are the same points we used previously. Whatever, doesn't matter. If I'm given these 3 points, how would I parameterize the plane that they describe? Well, I know how to parameterize planes. We parameterize planes with a formula that looks like this. I just need to start at some point. I'll pick A. And then I need to have some vectors that are parallel to the plane. Well, these vectors here will do nicely. Again, those are the pairwise subtractions. Those are my direction vectors, of which I'll be taking those scalar multiples. So just plug it into the formula that we just talked about, and there's your parameterization. Everybody good? All right, the last thing we'll do for today is again, I'm going to wave my hands at something here. This is, I think, all pretty readable. This is discussed in detail in the book. I have kind of hit some highlights in what I've written with all these, distance problems, we call them. For example, here, how do you find the distance between a point and a line? And side note, when they say distance, they mean the shortest possible distance. That's always implicit. So how do you compute that distance? And you play certain games, and these are the objects that you would play with to compute this distance. And again, discussed in the book. Here's a different way to do it. Here's a different kind of a problem. If you have two parallel planes, you want to find the shortest distance between two parallel planes. It's a different use of some different tools. Anyway, it's all just kind of fun and games with the objects that we've already discussed. So make sure to read through these and familiarize yourself with these ideas. call it a day. All right. See y'all later. Have a good one. Yeah. My pleasure.